We will consider another way to calculate posterior distributions in the case of intractable priors, so we don't have a conjugacy. And we will look at the Laplace approximation. The idea of Laplace approximation is relatively simple. So let's say you have a posterior distribution, and you don't really know the posterior distribution, but you know the product of prior and likelihood. And you know that your posterior is proportional to that. And you don't really know normalizing constant. So what we're gonna do, so let's say this is our parameter theta that we're trying to estimate. Let's say we have a just single parameter. We're gonna look at the univariate case. And that's our prior times the posterior times the likelihood. So that's a function that is proportional to the posterior. And so let's say it has a shape like this. And Laplace approximation will find the point where the posterior, or function proportional to the posterior, reaches its maxima. So we're going to call it point. Actually, to be consistent, let's use x as a variable, because that's what I use in the notes. So we're going to have fx and x0. So x0 is the point of maxima. And then what we do, we just approximate this curve with a normal bell curve. So, and we will center this normal bell curve at x0. And so we know the mean. So we approximate the prior times likelihood with normal bell curve. And the center of this normal bell curve is at x0. And the next parameter that we need to calculate is the width, the variance of the bell curve. And the way we're going to approximate it, we're going to basically calculate the second derivative. So let's call this function h of x. So we're going to calculate the second derivative of h of x0. And we're going to use basically the curvature. So a second derivative of this function h gives us the curvature at this point of maxima. And we're going to use this as an approximate for the variance. So it's going to be 1 over h prime x0. So that's it. That's the basic idea of the Laplace method. Now the question is, why it works, and we'll spend a few minutes on that. So let's consider Laplace approximation. First, we want to calculate an integral of this form, integral over a and b, and the function, the integrand, is exponential function of m times h of x. And if we look at the ratio, so let's introduce the function f, which is exponenta. That's our integrand. And looks like, let's look at the ratio of this function at the point of maxima. So x naught is maxima point here, over f of x. And we will see that's just an exponenta of m times h of x0 minus h of x. And the point of this little calculation is to show that the ratio, so this ratio will, since x of x naught is the maxima, then this difference is always going to be a positive number, and further away x from x naught, the larger this number becomes. So the ratio goes up as x moves away from x naught. Or in other words, we can say that the mass concentrates at around x0, And the larger M is, the more stronger this concentration. All right. So then let's look at the Taylor's expansion of h of x. And we will do Taylor expansion after the quadratic term. So that's, and we're going to do expansion at around x0, at around the maxima point. So it's the value of the function at x naught, plus the first derivative times the difference, plus 1/2 the second derivative times the difference squared. And then we have this term r, which is proportional to the quadratic difference, cubic difference between x and x naught. And since x naught is the maxima, it's a stationary point, the first derivative of 0. So we can just remove this term here, and we also remove the r, and we just say that hx is approximated by the value of h at x naught, then added 1/2 second derivative times the quadratic term. And if we can plug this back into the integral, we will see that exponent of h of x of 0 does not depend on x, so it goes in front of the integral. And what we have under the integral is this term, that's the integrand. And if you look carefully at it, you actually will see that it looks almost like normal density or proportional to normal density function. And if you take normal density with mu equals to x naught and variance equals to -1 over m h prime prime x naught, then what you have under the integral, the integrand, will be the functional part of the normal density minus the normalizing constant. So it's actually called the Gaussian integral. We can integrate it, we can calculate, and we know that it's you remember it's square root of 2 pi sigma squared is the normalizing constant for the normal. So it's 2 pi times the sigma squared, and sigma squared is -1 over m second derivative of h at x naught, and then we take a square root of that. So, and if we plug everything together now, so let's say we want to approximate an integral over some function g of x between, let's say, a and b, and we just put h of x to be the logarithm of that function, then we can approximate it by e to the m times h naught times this normalizing constant. And this is just g evaluated at x naught. So that's the expression we have for the integral. What we have at the end is that integral of this function g can be approximated by the value of the function g at the maxima times the normalizing constant, and this normalizing constant just depends on the curvature, on the 1 over h prime prime x naught. So that's the Laplace technique to calculate the integrals. And essentially what you do, you approximate it with a square function. You take the maxima, you approximated this maxima with a square function, and then you integrate the square function. And then that's how Laplace approximation works. And another note on m here, so you see that the resulting approximation will have this type of variance minus, actually that should be plus here, -1 over m h prime prime x0, and the larger the m, the smaller the variance, which means that this function becomes more and more concentrated at around x0, and then the larger the m, the better the approximation works. We know that because we want this mass to be as much close as possible to the center or to the mode compared to the tails. If you have large tails, the normal actually doesn't work very well. We know that normal has thin tails. So in this situation, approximation won't be that good. So approximation works well when you have low variances in this likelihood times the prior function. Or in other words, when this curvature h prime prime is a large number, large negative number. The second derivative was always negative at the maximum. All right, so, and now we can apply this to calculate the posterior expectation under the a Laplace approximation. I'm not gonna go through these calculations, you can follow them yourself, but the point here, if you try to calculate the expected value of parameter theta, and theta is the posterior of the distribution, so the distribution over theta given y, where y is the data, so it's the likelihood times the prior. And if we know the mode of the posterior, then the expectation becomes just the mode, which again something we would expect because we approximated with a normal distribution. Normal distribution mode and expectation is the same location. Let's look at an example and apply Laplace approximation to Poisson gamma model. So we have the Poisson likelihood and we have the conjugate prior in this case, gamma prior for the mean parameter of the Poisson. In this case we do the conjugate example, so we actually can compare the analytically calculated posterior with the Laplace approximation of the posterior. So this is the density for the gamma function, and we know how to calculate the posterior. The posterior distribution also will be gamma. We have a conjugacy, and the shape parameter is just y plus a, where a is the parameter of the prior, and the scale is 1 plus 1 over b. Again, the b is the scale parameter of the prior. And let's say we observe y equals to 2, and we will so that's make posterior is the function that basically calculate this density of the gamma distribution with the posterior values y plus the prior shape and 1 divided by 1 plus 1 plus of the scale. And let's say we start with a equals b equals 3 in this case. That's our prior assumptions. And if we calculate the posterior in this case, that's how it's going to look like. So that's the prior distribution over the parameter mu given in the dashed line, and that's the posterior. And remember the data set that we observed was y equals to 2, so that's the point that we did observe. So we see that the model did the correct thing. It pulled the posterior towards the observed data, and so we're gonna calculate the Laplace approximation, and since we know that the posterior is gamma, we can calculate the mode without doing any optimization. The mode is actually 3.75 in this case, and then we're gonna calculate the width. And once we fit the Laplace approximation, this is the red curve here. So I see we get a relatively close approximation. Laplace does a decent job. And now let's look at another example. And in this example, we actually don't have the analytical posterior, so we don't have much to compare with. Now we have a normal likelihood here, and we have normal prior for the mean and log normal prior for the standard deviation. This is not a conjugate case, so we cannot calculate the analytical solution here, and we just generate the data here with mean 10 and standard deviation equals to 5, and that's the histogram of the data. So most of the observations are around this mean equals to 10. And so let's do the calculations. We're gonna calculate this. We're gonna call this function model. So model will just calculate the likelihood times the prior. Okay. Actually, log likelihood times the prior. So log of the likelihood times the prior, and it's going to be proportional to the log posterior. And again, we take the log, so things become more computable. We have sums versus the products and calculating the posterior mode becomes easier computationally. And you remember the mode does not depend whether you take log or you do not take the log. Log is just a monotonically increasing function, so it doesn't change the solution to the maximization problem. And so log likelihood is just the sum of the normal density, and we specify that we take in a logarithmic scale. So this is the log likelihood, and then we take log likelihood and add the logarithm of the prior for parameter mu, and then logarithm of the prior for the parameter sigma, and this is our log posterior, or function that is proportional to the log posterior. And then we're just gonna use optimization method to find the mode of it, or the maxima. So we start with mu equals to 0, sigma equals to 1, and then we optimize with this initial value this model. And let's look at the solution. So that's the solution. Mu equals to 10.7 and sigma equal to 4.6. So mu sounds right. And the posterior for the sigma 4.6, and we started with equals to 5. So that's actually sounds good. And now we need to calculate. You remember the covariance is h second derivative raised to the power minus 1. And in this case, we have two parameters. So second derivative is actually Hessian matrix evaluated at this value x0, the value of the maxima, and then we have to take inverse of it. And so that's what we do. The optimization function finds the Hessian for us, and fit Hessian is the value of the Hessian at the maxima, and actually it's minus this inverse. And then the solve basically does the matrix inversion for us. So the covariance matrix is going to be negative of the inverse of the Hessian, which is, so you remember the Hessian is a positive, it's a definite matrix, and the inverse is the positive matrix. So we invert the positive matrix. So that's the Hessian. That's our covariance matrix for the normal. And so we have everything we need. We have the covariance matrix, and we have the mu parameter. And now we're just going to sample from it. We're going to generate 10,000 samples with the parameters 10 and 4.62 for the mean, and the covariance matrix given here. And that's the histogram for the first value for the mu. Again, it's centered somewhere at 10 point something, 10.7 in our case, which is close to the true mean that was used to generate the data. And sigma is centered at 4.76. So it's also close to this value 5, which was used for the true data to be generated. So Laplace approximation did a relatively good job approximating this posterior and allowing us to generate samples. So find the mean and find the variance. And let's compare it with a Hamiltonian Monte Carlo, but instead of implementing Hamiltonian Monte Carlo, we just used this BRMS package to do that. And so let's look at the Hamiltonian Monte Carlo posterior. So it's actually, so Hamiltonian Monte Carlo gives us number slightly greater than 10. And in this case, yeah, we actually had 10.7. So it's a very similar number. Histogram actually does look almost normal for the sigma parameter, and for the intercept parameter for the mu. That's our mu here. And for the sigma, it's centered at around, looks like also 4.7 here, so slightly left of the 5. But the shape is now different. The shape is not normal. You know, it has heavier right tail compared to the left tail. So this shape is different from shape of bell curve that is assumed in Laplace approximation.